Yes, sir, you can start, sir.
Right, thank you very much. So this is live session one in Foundations of Continuum Mechanics. My name is Gaurav Bhutani, and the intent of this session is to clarify the questions and concerns. And what we have done is we have planned for four live sessions. The first one is going to cover lectures 1 to 6, that is the first half of the course, and then we'll have 2 to 3 more live sessions where we'll cover the other topics as well. So I thought that this is a good time that many of you would have gone through the first 6 weeks and would have a significant number of doubts related to that. So we had floated through NPTEL a sheet with list of questions, and we got one reply there with a couple of questions where I'll open that. Give me a second, and then we'll address the ones that concern weeks 1 to 6 in that. Right. So we got some questions or some suggestions from Raf. So I think Raf is here. So the first question you have is, could you please provide more exercises that will be helpful in the exam for further learning? Because weak assignments are relatively easy. Well, that's good if they're easy. I mean, we can provide more problems, but it seems we have provided plenty. But what I can suggest to you is that there is a very nice book on problems that's by the same authors from whose textbook we are using, Mace and Mace, and that's a Shams problem series. So I'm not sure if you have access to that, but it's a very nice book. We usually design problems from that book on Shom's series on continuum mechanics. It's by the same authors, Mace and Mace, whose book we are using as a textbook. So I'll suggest you can try problems from that, the very good problems of different difficulty levels, and they will definitely help you clarify the concepts as well as with helping in the exams eventually. That's the best I can do. I mean, providing more questions is if I do that, I'll do it from those. But you can always get in touch with us over the forum. I have replied to all the questions people had from lectures 1 to 6. But in any case, you're welcome to contact me over through the forum, preferably. If not, then you can always send a direct email at my college ID as well, whatever suits. And we can help you shortlist a few problems from the book. And even the textbook Mace and Mace has a very good set of problems as problems at the end of each chapter. And we have used a couple of them for tutorials as well in this course. Right. So we only have one participant. So I'll just ask the host, are the participants allowed to talk in this session? The host from NPTEL, who's that? Can the participant just talk? So you want to use the chat box? Okay. So you can do that. So the next question you have is the idea of reciprocal bases. Okay. We did not get into that. Actually, that's beyond the scope of this course. So this course, we clarified in the beginning that we'll be working with indicial notation in Cartesian coordinate system. So reciprocal bases usually come up when we talk about non-orthogonal bases or situations where you have other coordinate systems which are curvilinear coordinate systems. And then you get into the ideas of differential geometry, where we get into advanced ideas of geometry rather than focusing on. So this is the first level's foundation course in continuum mechanics. So we do not get into the idea of reciprocal bases. Basically, reciprocal bases will be the same as your normal bases in Cartesian coordinate system. So there's no idea of contravariant or covariant here in this course. So what I'll suggest to you is that for the scope of this course, there's no need for these non orthogonal or non-Cartesian coordinate systems. So these ideas do not concern us in this course. That's the best I can do. I hope that answers the question. And usually you'll see that even in the textbook, they never talk about these non-orthogonal coordinates. So the ideas geometrically get the geometrically the ideas get a bit complex with curvilinear coordinates. So we're not getting into the differential geometry ideas here. Right. Next question is regarding material derivatives. So we'll cover that in the next session, which will I think be in the next week, because I wanted to focus on the first 4 weeks, that is the foundations of the tensor algebra and calculus and some foundational mathematics ideas, and then weeks 5 and 6, which were on stress tensor and related concepts. Then beyond that, we'll enter into the ideas of kinematics, which is what is the third question about the material derivative, acceleration, and so on. So I'll answer to these questions in the chat if you have them. I think you had somebody had questions in the chat as well. But for this live session, I'll suggest we do it next week because we wanted to focus on this session for lectures 1 to 6. Would you want me to go through? I mean, there's only one member in the meeting apart from the learners list. Do you want me to go through a recap of the basic concepts in the course in case or clarify some ideas which usually confuse people? So we collected a list of questions we had in the chat, and we thought of clarifying those ideas, but those people have not joined, it seems. So this is for Raf. Do you want me to go through some ideas from the basics? Right, sure. So then what I'll do is I'll go through a list of topics that we had shortlisted. Let me open that. To help with the material, I'll open the lecture material. We had combined all the PDFs, so it's easier to browse through that. I will share my screen. So, can the host please allow me to share my screen? It says host has disabled attendee screen sharing. And the host from NPTL, can you please allow me to share my screen? So I'm still waiting for them to respond. So in the meantime, I think in the interest of time, I'll just start talking about the ideas. So one was, I think we've clarified the use of Cartesian coordinates only. Next is there was some question about the use of repeated indices. So let's see if I can share. It's much easier if I show you the term. But when we are using repeated indices, and that's one of the major learning outcomes of this course in the use of indicial notation, sometimes we have two terms. So you can think of it as, let's say, UIVI, where I is a repeated index, and then we say plus, and then we have another mathematical term, which could be, let's say, WIVI. So what we see is that we have two mathematical terms here. One is UIVI, and then we add another mathematical term, which is WIVI. So I is a repeated index in both of these terms, but it has to be handled separately. So there was one confusion in the chat group. Somebody said that why can't we write it as summation over I and then we take both mathematical terms together? Yeah, I've been allowed to share my screen, so let me share it now. So I hope my screen's visible now. So let me browse through the topics and then I'll stop wherever we had concerns. So we started this course with the discussion on the ideas of the applicability of continuum hypothesis. And this is where we talked about the idea of Knudsen number. And then we moved on to the mathematics, the tools we require to discuss the ideas of continuum mechanics. And that starts with tensors. So we started talking about the definition of tensors, the number of components we need to define an nth order tensor in a Cartesian coordinate system. We have to be clear about that. We talked about the coordinate system, and then we talked about indicial notation, which is a very powerful notation, and that's again one of the major learning outcomes of this course, where we learn how to use this notation. We moved on to nth order tensors, which has 3 to the power of n components in a 3D world. And we said that unless we specify otherwise, the world is always three dimensional for the purpose of this discussion in this course. We always go from symbolic to indicial because many things are discussed in the symbolic notation, which has its own benefits. But for the interest of the notation, indicial notation in this course is preferred, and it's very powerful when working with the algebra and calculus of tensors. We talked about summation convention, which is again a very important and a very powerful tool. We talked about the definition of the summation rule, and this is where some questions arose. So let me go to a list of problems and then I'll discuss that. So if you look at the problem here on the top, which is UIVI plus VIWI. So when we apply the summation convention here, we always have to go to the definition, which says that we always apply the summation convention or the summation rule on each term by term basis. So we have a first mathematical term, which is UIVI, So we apply the summation rule to that term first, and then we apply the same rule to the second term. Okay, so the confusion usually is that we apply the summation over both the terms, but that may not result in the same thing because I is a dummy index. Now, in this case, it may just happen that we'll get the same thing, but if you have multiplication happening in some situations, it could be a problem. So it's always convenient that you take the repeated index in each mathematical term and deal with that separately. Just to clarify, it may or may not result in the same thing, but the way it works is you apply the summation on that repeated index in that term separately and not over all the term. But if they're linear, then they just add up. Right. After this, we move on to other mathematical tools we require, such as Kronecker delta and the epsilon or the permutation symbol, which basically help us with dot product and cross products respectively. So we discussed a couple of problems on the use of Kronecker delta, and then we moved on to the tutorial for that week. I think the use of Kronecker delta was quite clear. So the next we moved on to the permutation discussion on permutation symbol, where we talked about the ordering, which helps us with defining cross products in the initial notation form. And then we discussed the epsilon delta identity, a very powerful identity when simplifying expressions in mechanics. And then we use this first for vector operations, and then we generalize the use of these operators for the use of these symbols, the Kronecker delta and the permutation symbols for tensor operations. And during this, we started writing expressions in what we call the misuse notation, just for the purposes of this course, because whenever we look at terms, especially terms which are higher order tensors, we see that we stop writing the basis components, that is ei, ej, and so on. We simply write the final term. So let's take an example somewhere. So here we have in this in the third line from the top, we have ui, vj, ei, ej. So ei, ej is uh, the basis corresponding to ui, vj. So we'll have 9 terms in total. But what we do is we simply write, uh, go back. So we simply write this as ui, vj. We get rid of the ei, ej, and that sort of obvious that it's implied that we have two free indices. So we'll have EIEJ. There's a question. Could you please clarify the misuse notation? I saw that some books keep dyad product even in tensors. Right. How to correctly. Right. So let's look at this particular case where we define the dyad of two vectors u and v, which is the outer product. So here we see that we define it as ui, vj, ei, ej. So if I was to simply expand this over I and j, I would get these 9 terms, the sum of this 9 terms in this case, which is this. So these 9 terms, I mean, just like we write vector as a sum of 3 terms, we have 9 terms. So there are 9 components of this second order tensor that we have here. Now, if we take the analogy with vectors, like we have u1, e1 plus u2, e2 plus u3, e3, then whenever we write UI, that sort of, I mean, it's a notational understanding which we call the misuse notation, where we say that UI could mean U1, U2, and U3. So I could call UI as simply the whole vector. So UI technically is the correct way. So you can always write things in terms of the bases, that's EI, EJs. But even if you remove that, it's sort of implied when we use the misuse notation, and that's more or less the standard. But as you said, that many books keep them, just to be clear about it. So we can take an example where we do not use, where we use the misuse notation, and then we try to see what is a parallel with the basis that we have in that case. So, I mean, when you want to put in basis, you simply add the basis. So let's look at an example. So you ask, write the curl. Okay, so let's go to tensor calculus then. Right, so let's talk about the curl of a vector. I mean, the idea of curl of a vector actually comes from the cross product between two vectors. So it's better we, because it's just a vector operation. I mean, curl as such is simply an operator being applied. So let me actually go back to the cross product, where we will then uh, use and not use the misuse notation. Right. So this is the cross product between two vectors. So here we have u cross v. So we'll write, I mean, in the proper way, without the misuse notation, as ui ei cross vj ej, and then we say that ui and vj are simply indices in this, the way that we've written. So they are just numbers. I mean, they could be any, depending on I and j values, they could denote different numbers. So we can take them out of the cross product operation, and all we have is the cross between the unit vectors ei and ej, which by definition of cross products is written as e epsilon ijk ek hat. So that's the second last line here. And now this is what you say is the proper way to write the cross product between two vectors with the basis written ek hat. So this would expand, I mean, to vectorially speaking, to something times e1 hat plus something times e2 hat plus something times e3 hat. Now, if I just get rid of ek hat and call it the misuse notation, in that case, I'll have one free index, that is k. So if I put k equal to 1, that gives me the first index of that vector, or the first term of that vector. If I put k equal to 2, that gives me the second term in the vector. And if I put k equal to 3, that's epsilon ij 3 times ui vj, that gives me the third term or the third component in the vector. So that's an understanding that we are, just like we write the vectors as u1 comma u2 comma v3, we simply write it as ui, which means, so this is a notation that we prefer to use. Now if you take the curl, then again With the curl, it's you have ui vj here. If you have the curl of v, then it becomes del by del xi of vj. So it's, I mean, if there's any confusion, you always should go with the complete notation where you write the unit vector or the dyad of those vectors. But it's very common that books or people tend to get rid of that and use the number of free indices to denote the order of the tensor. It can be confusing in the beginning, but when you start using this as a notation, it becomes much more convenient. Remember, I mean, the idea of notations are that we can make things compact and easy. So removing the bases makes the terms more compact. There was one question regarding the matrix notation, which is a very common question when it is introduced for the first time. Let me go to the lecture on matrices here. So the question was that when we are writing product of matrices and vectors, let me take an example where we multiply a matrix and a vector. Yeah. So here in the last line, we have aij times ej, which is a multiplication. If you write in the matrix form, that's the matrix A multiplied with a column vector e1, e2, e3. So the question has been that how do we figure out whether we write the matrix or the vector in the um, row vector form or the column vector form. Now, to that, I always say that you work with the initial notation because the representation of the matrix in the I mean vector, particularly in the row vector or the column vector, depends on how we are multiplying things. So if we were doing the multiplication in a sense where the vector was on the left, so let's say we had ej times aji, now that would be written as the row vector e1, e2, e3 followed by the matrix A. So the representation of things in the matrix form are just to sort of agree with the way they are multiplied, and that is much more clearer in the initial notation, at least the way I see them. So writing a vector in the row form or the column form, that always is based on how we or multiply things in the initial notation. So I always suggest you work with the initial notation and then we write the corresponding matrix form. Okay, it was your question about this. Okay, good. So I think it clarifies, hopefully, that the representation in row and column forms, it's dependent on how we are multiply things, and that's much more clear in the initial notation. So matrices are just for the representation of the multiplication. See, ultimately, it's all. I mean, ultimately, when you simplify or expand the whole expression, that is what we are representing. Now, how do you reach that final representation? That depends on the various ways to denote things. Initial is one, matrix multiplication is the other one. But I suggest to use the initial one notation and then see the correspondence with the matrix after that, not work with matrix. When there are subjects where people work with matrices first and then represent as initial, that is what you did probably in school when we learned matrices. But here we are just trying to see the matrix notation as a parallel to this notation. So there is one other concern that was there was regarding the dyad of two vectors. Let's go back to that. So this is the dyad of U and V, where so let me discuss this and I'll come back to the question that is being asked. So when we have dyad of two vectors and we represent that in the initial notation, just trying to see if we have that somewhere. Yeah, so we have it here in the bottom. We have UIVJ, EIEJ. So we say that dyad is not, when you cannot commute the dyad, in the sense that UV is not the same as VU. Now, if you look at all the terms, remember EIEJ. So this basically boils down to the understanding of EIEJ, that's the basis, is not the same as EJEI in the outer sense. So EIEJ is not the same as EJEI, and that is the reason that the dyad is not commutative. But still, if I write the indices UIVJ in this case, then they represent numbers. If I'm not using the misuse notation, so in that case, what I'll see is that I mean U1 V2 will be the same as V2 U1, because U1 and V2, they are just numbers being multiplied, and a multiplication of scalars is commutative. But if I look at this whole UI, VJ, EI, EJ, then if I was to write as UJ, VI, EI, EJ, that would represent something else. So if you look at the matrix notation here, we have it here. So in one case, we may have a term U1, V2 as the term in the first row and second column. In the other case, we'll have the term U2, V1 in the, or if we write the other way, V1, U2 in the first row, second column. So that way is it is not commutative. So that's usually a confusion as to the commutative nature of the dyad and the indicial notation. So remember, it's UIVJ versus uh, VIUJ. If you work in the misuse notation, so UIVJ is not the same as uh, VIUJ in the outer sense, because they denote the symmetric terms. The one's the transpose of the other, so to say. So they're not the same. So let's go through a question that you have written. In simple terms, it's relatively easy, but when, for instance, you transform one tensor between coordinates, it's hard to figure out what transform uh, the matrix used indicial or transformed. I cannot see sometimes proper vector operation, matrix analog of what we did. Right. So transforms are actually, you're right, easy to visualize when you write the matrix form, because that's how we understand, or no, that's how we have learned the idea of transform. But we have to get used to working with things without visualizing, because we can visualize up to 2 dimensions. But when we try to go to three or n dimensions, for example, we work with situations where we have a fourth order tensor, which will eventually come when we talk about the rheology aspects. So there, it's very difficult if you try to visualize the transform of CIJKL, or you try to see the symmetry of CIJKL into any two indices. I mean, if you look at a matrix and we say the matrix is symmetric in the two indices I and J, it's much easier because we quickly visualize the transform is the same as the matrix. But if we work with orders higher than, I mean, up to three, maybe people can visualize with good visualizations. But beyond three, I mean, I don't even know if it's humanly possible to visualize nth order matrices, because we live in a world which is a maximum of three spatial dimensions. Uh, so the point is that one has to get used to these operations uh, in a mathematical sense of dealing with indices. So that's the reason we stress, and it comes with time. I mean, one semester is not enough to get a very solid foundations in terms of the use of indicial notation. Although the basics are clear, but with usage it gets much more concrete. So I would suggest to you is you don't try to visualize a matrix associated with a tensor, and try to work from the beginning to the end without any looking at the matrix analog, whether one, a two dimension, three dimensions, or any, I mean, two, a second order, third order, any nth order tensor. Then you'll actually force yourself to understand things in the more theoretical initial sense. That's the best I can say. I mean, I'm not sure how to help you visualize the matrices. But if you understand the initial notation and you have an expression, then writing the corresponding matrix notation is much more straightforward. So I personally do not think in terms of matrices anymore. I tend to think in terms of, I mean, I tend to work with initial notations. And then if I need the matrix representation at any stage, I just go from the initial to matrix. I would not work through the complete set of steps as matrix operations. So I'm not sure if I was able to help you with this question, but I would say the learning outcome of this course is not to be dependent on matrices or vector or the visual representation of those quantities, but to work with indices. Yeah, curl of a tensor. That's the next question. I'll just talk about curl of a tensor in general sense, and we'll talk about any specific questions as to why we use it in compatibility or how we define it in compatibility later. But that's a there are two ways to define curl of a tensor. I think one's called the left, the other is called the right way. I mean, left is in left and right hands. So what we gave you as the curl of tensor, I don't know which one we used, but you can always define like epsilon ijk sigma pj comma I, and you can also define it as sigma epsilon ijk sigma jp comma I. So there are two different definitions of the curl of a tensor. So if we work with indicial, we know which one we are using. With symbolic, again, if you there are books where they say that, I mean, nabla cross sigma, and they'll say bracket and then say left. Sometimes they'll say right. Okay, but that was that not the question? Okay, I think I understand the question. So epsilon ijk, epsilon ijk sigma pk comma j. I think the question is that in one we have k comma j, that's the third index of epsilon, comma the second index of epsilon, and then in the first case we had defined epsilon ijk sigma pj comma I, which is the second index of epsilon, comma, the first index of epsilon, right? Is that the question? Right. But that doesn't matter because, I mean, you can always, as you said, that you can shift between 1, 2, 3, 2, 3, 1, and 3, 1, 2. I mean, let's look at the first one. We have epsilon ijk. I mean, you can work through it if you have a pen and a notebook. Epsilon ijk sigma pj comma I. Now, what you can do is you can write your epsilon ijk as epsilon kij, and because you know that epsilon ijk is the same as epsilon jki is the same as epsilon kij. If you write this as epsilon kij times sigma pj comma I, that's exactly the same form as what we have in the second case, except that we are using different indices. So then you can write your change the repeated index with something else. Does that was I able to answer or explain that? And we do that a lot. We do that very often, where we tend to write epsilon ijk as epsilon jki as epsilon kij. But yeah, I think, and in many books you will see that they'll write the cross product as epsilon ijk ui vj. In some cases they'll write uj vk. In some cases they'll write uk vi. So once you complete with the bases for the third index, it will all expand to the same thing. Right. Now, for the application of this to compatibility, I'll just request you to please wait till next week when we talk about compatibility. If the question is about the application of this curl and compatibility, and we'll take it up there. But if you have any question in the chat, I'll just write the answers there. But the use of left and right handed curl is something I'll clarify when we talk about the compatibility, because it's a very confusing thing, that derivation especially, and one needs. I think many people may have that question regarding the compatibility derivation. So I'll go through the derivation with why we chose. I saw that question on the chat, that there was a question on why we start with, I think probably that was your question, why we start with the curl of sigma and how do we assume that. So if you're okay to wait for a week, then we'll discuss it in detail in next week as per the announcement. But if there's any question regarding the definition of uh, the curl of sigma, we can take it up here. So the choice of right or left curl, right-handed or left-handed curl, is our choice. It's not um, it's, it's not forced upon us that this is the particular curl, but which choice to take is dependent on when we are using that. So for the first 4 weeks, it's just a matter of if we give you a definition, then how do you proceed further with that? But I'll take it up definitely next week when we talk about the kinematics part. And usually it's the trickiest week where we discuss all these things. I have two more points that I want to take it up here. Probably that will clarify things further. One is a very, very confusing thing that many people have. So I will definitely discuss that first. Let me see an example of that. That probably was when we discussed the Moore's circles. maybe when we define the diagonal matrix. Let me find a problem and then we'll explain that or clarify that idea. Right. So this is another point, a portion of the. This is another idea that confuses many people. Now, this is where actually the matrix notation is more convenient than the initial notation. But sadly, the initial notation has no elegant way to explain this, as far as I know further. So let's look at the last expression. We don't worry about what's happening here in terms of the concept. But the last box term says sigma star ij, which is the I comma jth term of ijth term of a tensor sigma star, is lambda bracket j times delta ej. Now here it may appear at first that j is a repeated index, so we should sum on it. And that may not be the right thing here because we are not using j as an index for repeated index, because otherwise the number of free indices on the right hand side will be 1. On the left hand side we have 2. So this equality is not valid. We can't equate a second order tensor to a first order tensor. So what's happening on the right hand side is here we apply the expansion. So delta ij has two indices I and j, and when you expand this, when you write this in the matrix form, you write this as sigma star, let's say 1 1 is delta 1 1, and then you use the value of j that you used in the expression for lambda j as well. So this basically will expand to a diagonal matrix where you have lambda bracket 1 as the first diagonal, lambda bracket 2 as the second diagonal, and the lambda bracket 3 as the third diagonal, and all the other terms will be 0. So if you visualize in the matrix form, then it's much easier to gather it first, and then the initial notation makes sense. And this also comes up in situations where we prefer to work in the principal coordinate system, because when we work in the principal coordinate system, then our sigma star is represented like this. And then when you have the outer product or some sort of a product, inner outer product of sigmas and so on, then you have multiple lambdas and deltas getting multiplied to each other, and one has to be careful about that. So this is another portion where confusions happen. And if I take a contraction on this one, let's say I say I equal to j, so that becomes lambda j times delta jj. So the first confusion occurs that j appears thrice. But remember, j is not a repeated index when it appears in lambda. So j is not an index for summation convention purposes when it appears with lambda here. So delta jj would simply expand to delta 1 1 plus delta 2 2 plus delta 3 3. But since we also have a lambda j with it, it actually expands to lambda 1 delta 1 1 plus lambda 2 delta 2 2 plus lambda 3 delta 3 3. So that becomes lambda 1 plus lambda 2 plus lambda 3. So this again other is a point of confusion which I wanted to clarify. But if you look at how we obtain this, going from the first step to the other last, then it will make sense. But here I'll suggest to start with, you try to visualize things starting from the matrix point of view, and then you write the initial. That probably will help you understand if there's a confusion in the beginning of this notation. But again, with usage, uh, it becomes clear. But I still get confused with this situation where we prefer to work in the principal coordinate systems, and then we have a j or an index appearing with the principal values, which for summation convention purposes is not treated as an index, but it does expand. So it sort of tags along with the other terms. The easiest thing is you apply the expansion, but then when you expand it, you don't apply any rules. You simply put in the values of indices and you proceed. So that will make sense. So, one question was there, which I think was clarified in the chat, that we always define traction by taking an imaginary cutting plane through the point P, but sometimes we also define traction on a surface. Uh, so, traction is a general concept. When you talk about a point on a surface of a body, you can think of a cutting plane that's passing, in a sense that the cutting plane has a normal oriented with the normal to that point on the surface, and there's only one side of the cutting plane where you have body, the other side there's nothing. So cutting plane passing through a point P inside the body is a more general way, and if the point happens to be on the surface of the body, that's a special situation. But don't be confused when we talk about the traction acting on the surface versus the traction acting inside the body. Uh, it's just the same idea, except that we're talking about a special case where the uh, we are on the surface. So when we apply the net force integrals on force balances, then we tend to take the sum of all the surface forces, which results in the surface tractions. Right. One last clarification, which again I'll suggest. There's one confusion that occurs to many people, that when we write more circles, we have a physical plane and we have a stress plane. Let's take a picture for clarification in the more circles, and that's going to be the last discussion point in today's session. Let's take this picture where we have a physical plane and a stress plane. If I move from, let's take a problem. Yeah. So if I move in the physical plane as I depict on the right hand side, so let's say we have, so the meaning of physical plane is that if I say the red line x1 star vector, that's probably meaning that my normal to the cutting surface is oriented along x1 star. So if that is the case, then I get a situation, because x1 star happens to be the principal direction. So I know that when I slice the body in such a way so that the cutting plane is along the principal plane, that is, its normal is along the principal direction, then I only have a normal force or the normal stress sigma n. There's no sigma s. So that results in the point small a on the left hand side, that's on the stress plane. But the confusion appears when we say we are rotating from A to B. That is, we are rotating our cutting plane in such a way so that initially the normal orients along x1 star, and as we rotate it, the normal gradually moves towards x2 star. How does that result in the rotation in the stress plane? What is the direction of rotation? Now, usually we do not talk about the circles below the sigma and axis. That is, we do not talk about, we are not worried about or interested in the stress plane. in the negative direction, negative values of stresses. And the reason is because if we look at how we started the discussion on Moore circles, we said that when we slice a body through a point P with a normal n hat, that results in a traction, which is in some direction along the direction of traction, and um, we can take components of T, one along the normal and the other which is perpendicular to the normal in the plane of traction in the normal. So that's sigma S component. And the reason we developed the idea of Mohr circles is because ultimately we want to see whether some failure may occur or not. That is, whether my sigma n would be larger than the largest value my body could take, or whether my sigma s, and that's more interesting for us in general, whether that sigma s will cross a certain value, which may result in yielding or failure. So, if you think about it, direction of sigma s will not matter here. Whether the sigma s acts uh, to the left, as I've shown in the figure, or to the right, or to any other direction, because it's just a matter of acting on the plane. The direction is simply a convention we have used. So that is the reason we talk about more circles only in the plane above the sigma n axis. We're not even interested in what's happening below, because that just does not give any useful information. And from the concept of developing more circles. So I never suggest people to be confused about going below the sigma n axis at all. You work only above the sigma n axis for the purposes of uh, the working in the Mohs circles. So if we go above or below if I do a theta rotation and go up, or theta rotation and go down, my sigma n value will not change. What only can change is the direction of sigma s. But the concept of the direction of sigma s is simply the direction of the plane, which does not have any significance in the ultimate application of this idea uh, to the theory of failure or yielding that we use. So sigma s direction is more of a convention. In one convention, you call it negative; the other convention, you got to call it positive. But that physically does not change the picture. So I suggest that we shouldn't even get confused about that. Now, the only confusion appeared, I think, because we wanted to write this as a full circle. Yeah. So in plane stresses, because we only draw one circle, and we when we rotate, we have a point above and we have a point below. But my suggestion to you is that if you think of the implication of this in anything physical, there will not be any implication, because the way this sigma 1 2 will appear in the squared in the equations, and that's the reason we say that we don't even worry about working in the lower plane. I'm not sure if that helps, but I do not want to get into that discussion where they talk about the sign of sigma, because I feel that that is not a very useful idea, and it's better we only work with the upper plane and not worry about the lower plane. That's a clarification I wanted to give. I will not get into detail of clarifying why certain books talk about negative, but there are clarifications available where they say that depending on the convention, you can choose the lower one as positive, and that results in something. But that does not help us, because ultimately we end up squaring sigma 1 2 in the equations we deal with. So that sort of does not help in any way. So if you want, I can share with you some material on further material. But or you look for a, I mean, when you start applying more circles, you look for situations where the sign could matter for sigma, and then you may realize that it's not of that much of an importance. Right? Are there any other questions? I'm sorry, I don't want to get into this question of why certain books call sigma as a negative. Uh, the only reason we did that here is because we wanted to agree with the points on the circle, but a positive sigma 1 2 and a negative sigma 1 2 is just on the opposite plane, which does not help us too much. Think visually, they'll cause the same kind of motion in the body. Are there any further questions? Otherwise, we can close this session, and then whatever questions. Right. Okay. Let me answer it for once if you would want to. Um, if you want to guess the sign, you can go one convention says so you go opposite. So you go clockwise in physical, so that results in counterclockwise in stress. You go clockwise in physical, that results in clockwise in stress. That depends on the notation we are using. But the point is that the way we discussed more circles, we did not talk about the sign of shear in any way, the way it was formulated. So you can, I mean, think of how would you go clockwise from point A to B in the red coordinate system. You can only go counterclockwise. I mean, you go clockwise, you will travel 360 minus 90 degrees. So we are working in the first octant, and that results in a more circle, which is going to give us points in the positive region of the sigma s values. If you want one answer, then you can go opposite if you want, um, if that helps with the sign. But usually we do not worry about that. That's what my point is. Right. So let's close this session, and then in the next session we'll talk further about kinematics, which has a lot of confusion usually. So we'll clarify those confusions. And I also reply to the questions from weeks 7 and 8 on the chat, and then we'll take it up in the live session. And as I said, you can always get back to me over email if you have any further questions. Type something up on write something up on a paper. You can share that with me, and I'll be happy to get back and provide clarifications. Thank you very much, and I'll see you next time. Thank you.